Hi there. Today I'm going to talk a little bit about exponential growth and decay in terms of calculus. So before in maybe pre-calculus 12 or just on your own time, you learned a bit about how to model exponential growth and decay with equations, something like a equals a naught times, for doing interest equations, 1 plus I to the power of t, all that good stuff. So this is pretty similar. It's a pretty specific branch of calculus, kind of a topic to cover, but it's it's pretty important in business and modeling population of species and stuff like that. It's just something that is good to know. So how do we come up with these equations? Well, in pre-calculus 12 or maybe in like a class that's not quite dealing with derivatives and integrals, you don't learn as much about rates, you learn about actual quantities. So we can figure out populations just from rates, right? So that's kind of the whole idea of calculus is rates. So if we have the dA by dt, this is the rate that A is changing with respect to time. Okay, so if dA by dt is proportional to the species at the time or the population at the time, we say it's equal to K times A, right? So K is just some proportionality constant, right? This is a constant. And A is our population. So like I said, with let's say if we had the population of people, right? The population of people is typically proportional to the rate because if we have more people, this rate dA by dt is going to increase. The more people there are, the higher rate of growth of people in the world there is, right? So dA by dt in terms of population typically is K times A, right? Where K is a positive number. If K is a if K is a small number, like let's say K was negative, that means that this rate here would be negative because this would be like if K was negative 5, say, this would be negative 5A, right? This equals dA by dt. This is negative 5 times the population. So as the population increases, the rate actually decreases, right? So how can we use this to figure out actual quantities of population? Well, we use integrals for that. So if we have dA by dt equals Ka, if we divide both sides by a, right? If we're trying to solve for what k is, we can divide by a. So this is, if we integrate both sides, right? We take the integral. This is like 1 over a times dA by dt. Okay, and this is with respect to t, so it's dt. This equals the integral of k dt. All right, we're taking the integral both sides with respect to t. All right, now what's the next move? Well, we see these two dt's can cancel out, so we get the integral of 1 over a with respect to t equals the integral of k with respect to t. All right. Oh, sorry, this is the integral of 1 over a with respect to a because the dt is canceled. I don't know why I wrote dt. Okay, so what's the integral of 1 over a with respect to a? This is equal to the natural log, right, of the absolute value of a. What's the integral of k with respect to t? Well, we can factor out the k because k is a constant, right? So this is the integral of just dt, and the integral of dt is just t. So this is kt, right, plus c. Okay, so it's a few more steps here. If we want to get rid of this natural log and just solve for a, we can take, we can raise both sides to, so if we take e to the natural log of a, right, this is kind of how we can simplify it here. This is e to the kt plus c. E to the natural log of a, that's just from your logs unit, that's the same as a. Okay, e to the kt plus c, we can kind of split these off. This is equal to a to the kt times e to the c, right? Because if we multiply two exponentials with the same base, their exponents can add, and we can kind of split them off like this. Now that we have it in this form, we can use something called the initial condition. So a at time 0 is equal to e to the k times 0, right? Because our t is just 0 times e to the c. Well, e to the 0, right? Because this just becomes 0 up here. So e to the 0 is just 1. So a naught equals just e to the c. So instead of e to the c that we had up here, we can just write a naught. That's super important. We can kind of clean it up. So we can write it a equals a naught times e to the kt. Now, isn't that cool? The population of a, if it can be represented using a proportionality constant k up here, if it's proportional to the growth, it can be represented as the initial value of a times the number e raised to the power kt. Okay, so this is super important in exponential change, right, when we're dealing with rates. In my next video, I'm going to do all sorts of examples, but this is kind of how we set up this equation. And once we know this, it's going to make our lives a lot easier. So if you kind of followed through this derivation here, I know it's a lot of algebra, a lot of numbers, lots of integration. You're on the right track, and it's going to get a little harder, but this is kind of just intuition, and hopefully it made a bit of sense. I'll see you in the next video.